Where is it? Well, good morning. In fact, Steve and Sip being now at management level, as engineers, they don't know, in fact, why they have each other the best the best trajectory prediction system. And I'm going to explain you why. It's because the aircraft performance model, which is inside, obviously inside OTP, is the best one. Huh? So for that, we have within this activity, this action plan 16, identify a point, which is point 5 that Mike has presented at the in one of the first slides on how can we evaluate and validate at the same time existing present aircraft performance model, and if none of them matches our requirements destined to trajectory prediction, what can we do in order to improve them? So the presentation will be relatively short and will contain a few general items. Why do we talk about aircraft performance model? This is to explain to Steve and Sip what they can say. See if there are already existing some tools and metrics which are available in order to evaluate existing one and to validate them, such that we can make a choice in case we start a new activity which needs aircraft performance model. If not, build one. And that's what we have done within Action Plan. We have built this PAMPA platform, which is platform for aircraft performance model evaluation. And we plan now together within the AP16 with the US and Europe to run an experiment where we will evaluate different approaches to aircraft performance modeling. And fortunately, the answer will be in line with what I have started to tell you, although I'm not yet sure. Well, why do we talk about aircraft performance model? There is no real reason for that because every application has one, and often they are very happy with them, and they have been developed for that specific purpose. But when we arrive here on Monday, Mike has very nicely organized for us. We have never been in the tech center a visit to get acquainted with some of the main projects that you are doing. And of the 5 presentations I have been through, the 5 projects, I have spotted 3 of them which uses aircraft performance, which I guess uses aircraft performance. It was the display system replacement and the URED tool. URED needs a TP, and this TP has aircraft performance into it. Also, your OS system, which I have understood does the flight plan processing in order to detect the sector suite and the sector handover times and so on, must also use a trajectory prediction and, as such, has aircraft performance into it. We have also been presented the enhanced traffic management system, which does trajectory prediction over very long areas and from, I have understood, takeoff or at least initial climb up to the destination airport. And the last one that we have been presented was the target generation facility. There it's a simulation where aircraft performance are used in order to simulate in the best way the behavior of the aircraft. So this is not in our real activity, which is more trajectory predictor dedicated, but there is also a requirement for aircraft performance. Now, the question we often have is there accuracy known of any of the modeling approaches we are using? Okay, I can tell you that in Europe, we have exactly the same situation. We have several trajectory predictions approach, and we have also different aircraft performance modeling approaches. At least in the US, you are lucky you only have one administration. Eurocontrol has nowadays, I think, something like 32 member states, and we have so 32 administrations. So it's still a factor 32 more in terms of approaches to aircraft performance modeling. The other question we would like to answer is, which requirements do the aircraft performance modeling approaches existing today met? Well, from what we see in the field, we can say that they met requirements for open loop prediction, the technique which is used, by example, in ERET or in medium-term conflict detection in Europe, where we do a prediction from the present situation, assuming a given aircraft intent, and we just try to see where the aircraft will be in 5, 10, 15 minutes time with a given uncertainty. And most of them, if not all of them, the aircraft performance model which are used are only used in en route operational environment. So they only deal with the aircraft performance in non-clean configuration. However, if we think now of the increasing role of automation and what trajectory prediction should be capable of supporting in terms of new decision support tools, and on the other side, what our simulation platform should be capable to do, we can start thinking about much higher level requirements like air-ground compatibility. What's the compatibility between the aircraft performance model we use on the ground to feed the ground TP and the one used into the FMS? What if we switch to more intelligent tools which should provide you advisory generation. So systems which work in a closed loop, and when a problem is identified, like by example, when you do sequencing and metering, you need to generate an advisory. They are working in closed loop, you need to know additional knowledge. By example, what's the flight envelope for the aircraft at this given moment in time during this flight phase, such that you generate advisories which are flyable, and you don't start a discussion with the pilot, which will tell immediately the controller to drop the tool. The other areas that we have identified which could provide requirements which will be changing for aircraft performance model is also multi-sector planning. There we need to predict along longer areas like ETMS makes it, by example, but also we will need to do a lot of predictions in order to find a multi-sector planning strategy. And in Europe, we have a program called Gate to Gate, which aims at developing a consistent ATM system from brake release until touchdown. So there we must have aircraft performance model, which even should include ground movement modeling, such that we can also do planning of the movements on the ground, by example, to feed a departure manager system. Now, do evaluation tools exist for the aircraft performance model? In fact, from our experience, not a lot or nearly nothing. Often, or more often nearly, they are embedded in the production process. So they are part of the process of generating the aircraft performance model itself, the coefficients that you will put into your equation to emulate the behavior of the aircraft. They require normally very specialized know-how because they are specific to that type of aircraft performance model and to the process of producing it. And they are limited in the scope and the application, and they are application specific because they have been really developed at the same time that the aircraft performance model has been developed. So what should be the objective for such a platform where we'll be capable of evaluating different possibilities of modeling aircraft performance and choose the best one for our application, whatever our requirements are? The first requirement we have set is that we need to have a coherent set of reference data. So we should be capable of feeding the platform with a single set of reference data such that we evaluate the different aircraft performance modeling approach against the same reference data. If not, no comparison will be valuable, obviously. We need to be able to validate several models against the same reference data on the same platform, because if not, the work will be so duplicated that nobody will do it. We will stay with our own individual approaches. And if necessary, for some of the requirements, we would like to be able to compare different models against each other, by example, for some specific requirements like speed of calculation. If you think at these multi-sector planning concepts where we will need to compute hundreds of trajectories, and when we try to do a what-if, by example, to reorganizing flows of traffic, group change level or group reroutings, such a what-if tool may require, against the computation of hundreds of trajectories in a short time. So speed may be one of the requirements. So with that requirements in mind, we specified what should be done on the platform for aircraft modeling performance analysis. We should allow the separation of the reference data generation. So this is what we call the truth data. You can take that, by example, this is the data that we will get from the aircraft manufacturers. Not always, but this is the data we aim for. We should separate the comparison process, the process where we run the different models for the different, let's see, performance item with the same input data, and the evaluation process where we compare the output of the model and the truth data and visualize it and see, okay, where does this model perform, where does it not, how well does it perform. One of the basic reasons for separating the steps is that we may have intellectual property rules issue with the reference data as provided by manufacturers. We also have, on the other hand, graphic user interface issues. Somebody may like to visualize the results of the comparison in a way, someone's in another. So this is why we wanted to separate the thing. And we have decided to connect to the platform, let's see, two types of models. The ones what we call kinetic models, which are force-based, where we need to model thrust and drag. We have two examples of them. One is BADA, it's a European model built by Eurocontrol. The other is the CETAS trajectory sensitizer model. And we have also connected to it kinematic models. So kinematic model is a model where, let's say, for example, through a tabular approach or through a polynomial one, you model the rate of climb as a function immediate of speed, weight, altitude, and outside air temperature, for example. Just a few slides. So now the platform looks. So we have the reference database in yellow on the left. What has been done there is we have built a database which several tables for the different items, and we have also built the interface that you see here to different aircraft performance manufacturing programs. You see the main ones, obviously, in-flight for Boeing, Pepsi for Airbus. We also have FOSS for ATR aircraft. We also have Opal. But you can also enter paper data or data coming, by example, in Excel sheets. Through an interface, all that is fed into the reference database, into the reference table, and you need a reference data, reference management utility such that you know which data has been put in which table for which aircraft type and so on. Now, the most interesting part, if I may say so, is when we want to compare, we need to have different aircraft models interface to the platform to be able to compare them against the truth data and one against each other if required. So to that effect, we have built what is called SAMI, it's Standard Aircraft Modeling Interface API, such that we can, in the same way, connect different modeling approach to the platform. It's independent of the fact that you have a kinetic or a kinematic approach. So the interface is sufficiently flexible to be able to drive kinetic or kinematic approaches from the comparison engine, which is the one which runs in function of the reference data available, runs all the models for the different items that you want to compare. We store the comparison results in a separate database such that it can be taken away on independent as the platform itself, and obviously we do the result display. So maybe just to summarize, the benefits is the reference database is put in a reference database, separate reference database, which is documented. So you can use that for other applications if IPR rules permit. The comparison database also is separate after having running the comparison process, and it can be used for evaluation the results with other applications. Typically, one of the applications that Titan has been doing is using MATLAB to analyze what are the results of the comparison. And the SAMI APIs is the one which allows the connection of different aircraft performance modeling approaches to the same platform. How does the output look? I have just 2 slides of that. What you can visualize is you can visualize, by example, per function. In that case, I have taken the rate of climb during the CAS phase. You can visualize the output of the model for, by example, this is rate of climb in function of the altitude for a given speed, a given outside air temperature, and a given aircraft weight. You can visualize the output of different models. This is what we have here. BADA 3.5 is a kinetic one. General aircraft modeling one in green is a kinematic one. And the central flow management unit model, it's a tabular model. So you can visualize all the output for a specific function for given conditions against what is the truth data, which is this one here. And you can see already if that function really behaves in the right way compared to what the truth data tells you. But obviously, you can easily imagine that if you have to do that for every function, for all the different range of input parameters, it will take quite a long time, and you will probably have difficult to synthesize all that output in a single picture. So for that, we have used what it's called pivot table. This is something which comes from the Microsoft Excel. I found very clever approach is where you can present on a 2-dimensional axis. By example, this is the same output of the same function, rate of climb, for 3 different models. And you can present the output in function of 2 axes. Here we have taken calibrated airspeed, one axis, and altitude, the other one. And you see through it all the other variables, in this case, weight and outside air temperature. And you can decide with the controlling of the pivot which are the axes you want to see and which range you want to see. So we have used a color coding for the error, which tells you if you define a limit for the error. For the moment, we have implemented into Pampa 4 types of errors: average, mean, and average, maximum, and mean and maximum for absolute and relative error. And you can visualize for the different models with the same conditions what is its performance in terms of error through the whole data set. So by example, this means on this diagram that you can see what's the performance of the model in terms, if you compare that to the color coding, for all speeds, all altitude, and in the third dimension, if I may say that, all the masses and all the temperature. Now, you may already be interested in saying, yes, but below flight level 100, I am interested in speed which are at 250 knots or below, because I'm not really interested in this area of the diagram, because you normally will not fly 300 knot CAS below flight level 200, below flight level 100, because ATC restriction. So you can start filtering and start looking at the areas where it is more important for you to get good performance out of the model. The same thing after flight level 100, if for this aircraft, by example, nominal climb speed is 280 knots, is within this area that you should start looking about how good your model is and how it degrades in function of the other parameters affecting the output. So this is the main graphical user interface where you can really visualize all through the truth data and start filtering by layers which part of it you are more interested in looking at, because one are more standard operating conditions for this aircraft type and others are really not so common. Now, this has been done only for 3 aircraft types for the moment, just which will deliver with the Pampa platform. Within AP16 now, we are going to organize an experiment where we want to do that for more aircraft type, more aircraft performance model, and apply to it a more sophisticated metrics to try to better qualify the performance of the different model. So we will start with the pilot exercise soon. We will concentrate on jet aircraft medium and heavy type. We have Boeing and Airbus truth data, and we cover the different aircraft performance modeling approaches, kinetic and kinematic. But we need the metrics to capture the results and try to draw some conclusions of the quality of each of the models. So the metrics, which question do we hope to answer with the metrics? We want to know how well does a model perform at nominal flight conditions, and how does its performance degrade when we are going out of nominal flight conditions. Why? Because most of the aircraft, if they are not subject to ATC or other constraints, will fly around their nominal flight conditions defined by their cost index. However, if ATC has to put constraints, think about the sequencing and metering system for arrivals management, you will be interested in see how well the performance of a model evolves, by example, with the speed. If the speed is a control parameter, which is to be manipulated by the sequencing and metering tool. We would also like to know what is the dependency, how evolves the accuracy when we vary one of the input parameters, and this for the different one affecting the performance. And finally, what is the range of input parameters for an aircraft performance model which still guarantee a level of performance? And we plan also to do a small sensitivity analysis of the model. How well does it evolve with different variation of input parameters? But probably over what range of input parameters value is a given model, performance guarantee will be one of the metrics which will be the most important one, because it will be capable of providing you, of helping you in taking the decision, yes, this model is suitable for my application. What expected results? I think probably it's only the first question that we can already answer. No, we don't expect that it will be any perfect model which will be perfectly accurate over the entire flap envelope. But how accurate is it? How accurate is it in different areas of the flight envelope? And how accurate is it in the areas where we need it? Another question we would like to look at is, can kinematic models compete with kinetic ones? This is not only because we are engineers and we are fighting about different approaches. It's also in function of the sophistication of the aircraft performance model you will use, by example, in an application like a trajectory predictor. It has an impact on the sophistication of the flight script. If you remember SIP's presentation where you use a flight script where you describe what the trajectory engine should compute, by example, if you want to use a kinetic model where you use thrust and drag in order to have the accuracy and the flexibility you want, you also need to provide in the flight script information about which thrust settings are going to be used, by example, during the climb phase, during a cruise acceleration phase, or during a deceleration phase. If your trajectory prediction only requires a given level of accuracy which can be matched by a kinematic model, you will not need to provide that because it's inherent into the kinematic approach. It has already been assumptions that climb is done with climb thrust, descent is done with idle thrust. So that will be an interesting answer to see if both approaches can compete in terms of accuracy. And the other result, obviously, can we match with the result will we obtain the requirements which will come from the user? Okay, there, in fact, we shoot a little bit ourselves in our foot in the sense that in order to be able to compare the models, we have built this Pampa platform with an interface to different aircraft performance modeling approach, which means for this one now, you have no problem in your application if you apply that interface to switch from one to the other. So in the case the evaluation tells you this one is better than the other one, if we go to the API way of interfacing between your application and the performance model, you will have the capability of changing one to the other. So that will be an add-on deliverable of this work which is done. We plan to run this experiment now. It should be finished before the end of the year, although it only covers 4 or 5 aircraft types. We plan to do it because we are going to take Airbus and Boeing ones, heavy and medium ones. We expect at that moment to get already a decent answer of what are the capabilities and the performance of the different modeling approaches. And I have just put there a few points of contact in case you want to contact us. Thank you.